Hi everyone, here we are. We've made it to our last lecture. So we're going to skip over through chapter 19. Not going to go through too much of it, just the first couple sections and just pieces of that. So I'm condensing 2 lectures down to 1 lecture. And so you've heard me talk about oxidative phosphorylation. It's the last step in cellular respiration. So what is oxidative phosphorylation? What is the purpose of it? And how does it use oxygen to turn all the things that we created in glycolysis and the citric acid cycle into ATP? So we have only 2 learning objectives. And again, it's not all of sections 1 and 2, but just skipped over parts of sections 1 and 2. Section 1, we're going to learn how our electrons transported to oxygen in the mitochondria via the electron transport chain. So oxidative phosphorylation has a couple of names, just like the citric acid cycle has a couple of names. And a lot of times it's referred to as the electron transport chain because it's transporting or transferring electrons through a series of reactions, finally to oxygen. So we're going to see the reactions or the mechanisms of how these electrons that are with our electron carriers are carried to oxygen. And then we're going to see how a proton gradient that's created by this electron transport chain is necessary for the synthesis of ATP. So our end goal here is to create ATP. And so how are we going to couple energy stored in electron acceptors? And remember, our electron acceptors are NADH. We created many of those in glycolysis and the citric acid cycle. Our FADH2, we created those in the citric acid cycle and fatty acid metabolism. And so those electron carriers are going to create a proton gradient, and that's going to drive the synthesis of ATP, and that's how we're going to get the vast majority of our energy from these pathways that break down our macromolecules. So oxidative phosphorylation, it's when electrons from the reduced cofactors NADH, also sometimes NADPH, and FADH2 are passed to protons in the respiratory chain. And that's just when we have aerobic conditions and oxygen is present. We usually create NADH and FADH2 through stage 2 and stage 3. So this would be, if we look down here, this is stage 3. So stage 1, in our respiratory chain is usually glycolysis and the creation of acetyl-CoA. So you break everything down to glucose, remember, and the glucose gives you 2 molecules of pyruvate. So those 2 molecules of pyruvate are converted into acetyl-CoA, and acetyl-CoA goes to the citric acid cycle, and then that creates NADH and FADH2. And so now we're at stage 3, the electron transfer and oxidative phosphorylation, where these NADH and FADH2, these are called reduced electron carriers, are transported to the respiratory chain or the electron transport chain. And you're carrying these electrons finally to O2. We're creating H2O, one of the products of metabolism. And the energy that's created from this electron transport or transfer is going to condense together ADPs and phosphates to create ATP. So I just described the stages of glycolysis, but in stage 2, we would have acetyl-CoA coming from fatty acid metabolism, and also that goes into the citric acid cycle, and we will have many intermediates in the citric acid cycle. Remember, the citric acid cycle is a cycle, and along that cycle many of our amino acids can enter and create NADH or FADH2. So now we're on stage 3. We created these NADH cofactors. We created the FADH2. So how are they being carrying electrons, transporting those electrons to oxygen, giving us water, and helping to condense ADP and phosphate to give us ATP. Sometimes you would hear this steps of coupling electrochemical gradient with ATP synthesis as the chemiosmotic theory. So it's not called as much right now, but your book does refer to it sometimes as a chemiosmotic theory. And what is that? So we know that we're coupling energy created from the electron transfer or electrons transferred to fueling the synthesis of ATP. So we're going to look at this in two steps. The first steps requires 4 different enzymes. And in these 4 different enzymes, there are many pathways that you have to learn of how we establish an electrochemical gradient. And what we're going to do is we're going to couple the downhill flow of electrons. Remember, we have electrons that are being carried by NADH and FADH2. And those electrons are going to be transferred from NADH and FADH2 downhill to electron carriers that have a higher affinity for electrons. And the energy created from the electron transfer is going to create an uphill flow of protons across a membrane. So electrons are going to be carried from one molecule to another, and the energy created from the electron carrying or electron transport is going to create a proton gradient uphill across a membrane. All right, so then we're going to establish this electrochemical gradient where we have more protons on one side of a membrane than another side of a membrane. And so then when the protons flow back across the membrane, we're going to use that gradient to fuel ATP synthesis. So we're going to see two things. In step 1, we're going to transfer electrons. They're going to go across the membrane, and we're going to have a gradient across the membrane. Those electrons, sorry, not electrons, those protons are going to get back across the membrane. And when they flood back across the membrane, that energy is going to help to synthesize ATP. So before we get into the reactions that take place to help us synthesize ATP, let's talk about where it happens. And it's important where it happens in the mitochondria because the mitochondria has a very specific features of its structure that help to give us a lot of places where we can actually synthesize this ATP. So when we think of the mitochondria, this is something you've seen, a very cartoon picture of the mitochondria. You've seen this in 6th, 7th, 8th grade. It's a bean-shaped organelle. All right, so it has an outer membrane. And so the outer membrane is freely permeable to small molecules. So all the small molecules that might be created in the cytosol of the cell, we have many mitochondria in our cell. Those small molecules are permeable and can get into the mitochondria. But then they are stopped by the inner membrane. And so the inner membrane is impermeable to almost everything, including just a small proton. So the inner membrane does not let things get into the matrix of the cell. And so how do things get into the matrix of the cell? It's only through transmembrane proteins. So our transmembrane proteins or enzymes of the respiratory chain that we'll talk about are in the inner membrane. The inner membrane is folded over and over and over again. We call the folds cristae, and that increases the surface area. And so all this inner membrane that gets folded over and over and over and over again in the mitochondria contain the proteins of the respiratory chain and ATP synthesis, so we can have more physical space for synthesizing our ATP. So just imagine you have over and over again this inner membrane And within the inner membrane, we have our ATP synthesis proteins going across the membrane. So we can synthesize and we can let in and let out small molecules through those transporters or through those proteins that are not permeable to the cell. All right, so then we have our matrix. We're not going to focus on the matrix too much, but we saw that our pyruvate dehydrogenase complex, or our citric acid enzymes, our beta oxidation enzymes, they occur in the matrix. So you have things that are created in the matrix that have to get across the inner membrane space, and things that are created in the cytosol that have to get across the inner membrane space so that they can actually synthesize ATP. So we'll see how those proteins that transverse the inner membrane space are involved in synthesizing ATP. So we know that many of our metabolic sources provide electrons to our electron carriers. And our electron carriers are, again, our NADH, NADPH, or FADH2. And they are carrying electrons to the electron transfer chain, or we also call that oxidative phosphorylation. And that energy from electron transfer produces a proton gradient that provides energy for ATP. But when we look at the NADH, the NADPH, or the FADH2 that's created from metabolism, they are in different parts of the cell, and we're going to see that they have to be transported across that inner membrane that's impermeable to everything, because they are produced in different parts of the cell. And so if we look at, and this is not something you have to memorize, so I'm just kind of going over it briefly, just to show that you have a reaction in the citric acid cycle that from alpha ketoglutarate that produces an NADH. It's an electron carrier, but this one is in the mitochondria. But if we look at how pyruvate creates NADH and acetyl-CoA, this also happens in the mitochondria. But a reaction from glycolysis, and most of our reactions from glycolysis are going to happen in the cytosol. So this gap molecule that produces an NADH is going to happen in the cytosol. So you have NADH, and you have NADPH, and you have FADH2. They're all carrying electrons that are going to give us energy in the end, but some of them in the mitochondria and some of them in the cytosol. And how are we going to transport those electron carriers so they can transport those electrons through the inner membrane space? So we're going to look at how we're transporting those electrons through proteins in the inner membrane space so they can all be in one place so that it can actually create ATP for us. Okay, so again, in step 1, we want to establish an electrochemical gradient. We want to couple the downhill flow of electrons, moving electrons from NADH or FADH2 to other electron carriers. And the energy from that transfer is going to be coupled with the uphill flow of protons. So we have electrons sitting in our NADH. I'll just draw that. So this can be NADH or FADH2, either on the matrix side or the inner membrane space. Either side it is in. So electrons here, for instance, are in NADH2, and we want to get them into other electron carriers that we'll see. And so we're going to just go transferring electrons along. Transferring electrons is going to produce energy, and that is going to give the energy to protons into the intermembrane space. So we're going to see electrons transfer from NADH and also FADH2 to other electron carriers. When you do that, you're going to release a little bit of energy, and that energy is going to help to pump protons into the intermembrane space. And so this happens, let me just erase this. This happens in 4 different complexes. They have names that you don't have to know. So I'll tell you what the names are, but you don't have to know the names of them. We have complex 1. Of course, you know how to spell complex, but so I'll just say complex 1, complex 2, complex 3, and complex 4. And usually you see them with the Roman numerals, so make sure you use Roman numerals. And in each of these complexes, we're going to start with electrons being carried by NADH or FADH2. And so when we think of electrons being carried, we can think of them as, so this is an electron, and they'll have a downhill flow of energy, right? So the electron is being carried. And what are they doing when they go down here? They're releasing energy. Release energy. Okay. And when we say a downhill flow of electrons, instead of just releasing a bunch of energy and that energy fueling the synthesis of ATP, what we'll see is those electrons are going to be transported or transferred in a stepwise motion, releasing a little bit of energy at a time, going from one electron carrier that has a higher affinity for electrons than the next electron carrier, then the next electron carrier. And every time they stepwise transfer their electrons, they're going to release a little bit of energy. That energy is going to pump out protons. And so what we'll see mostly is in complex 1 and complex 2, we're going to transfer electrons from NADH or FADH2 to one electron carrier. And then in complex 3, we're going to take that electron carrier, and it's going to transfer electrons to another electron carrier that has even higher affinity, and that energy release is going to pump out protons. And then finally, in complex 4, we're going to transfer electrons to oxygen. So we're not just going from NADH to oxygen, which is our final electron acceptor. We're going through a bunch of electron carriers, all releasing a little bit of energy at a time. Finally, we're going to get the electrons to oxygen, and that's going to release enough energy to pump protons into the inner membrane space. And when those protons go back into the matrix, that's going to fuel the synthesis of ATP. And we'll see how that happens. Okay, so try to reorient yourself and think about the fact that we have these electron carriers NADH and FADH2. And these electron carriers are carrying electrons, but they're not keeping them. They're transferring them to other electron carriers, one complex at a time. So that's what we're doing now. We're saying we have electron carriers, NADH or FADH2, but right now we're going to talk about NADH. And you carried electrons from glycolysis, you carried electrons from the citric acid cycle or beta oxidation or whatever. And now you're going to dump those electrons into these complexes which have other electron carriers. And so now we're at the point we have this NADH and it's on the matrix side. You see this here, it's called the N side, and that means it's the negative side because eventually it's going to have a negative charge because we're going to pump protons plus charges out into the P side. But anyway, so we have this NADH, we created it, and now we need to dump those electrons, and we're going to dump them into complex 1. So complex 1, also called the NADH dehydrogenase, but we're just going to call it complex 1. It's going to transfer electrons. It's going to take those electrons. So what about complex 1? It's one of the largest macromolecular assemblies. It has 45 different polypeptide chains, and it kind of looks like an arm. So it's this big, huge complex. First, it's going to take the NADH and bind it on the matrix side or the N side. And then within the complex, it's going to first transfer its electrons to FMN. And we can just, FMN is very similar to FAD. It's a non-standard nucleotide. But the thing about FMN, it has a higher affinity for electrons than does NADH. So it happily takes those electrons. So NADH has 2 electrons in the form of hydride, and it's going to transfer those electrons to FMN. Also in complex 1, there are a bunch of iron sulfur centers. All right. So we'll look at that in a minute. But there are several iron sulfur centers that can take 1 electron at a time. So these electrons are bouncing from NADH to FMN. Then through these very complex iron sulfur centers, they're all taking electrons. Finally, we get to a cofactor called Q, and it's the final electron acceptor. So we've taken the electrons from NADH, we pass them to FMN, we pass them on to a bunch of iron centers, and then our final electron acceptor in complex 1, it's Q. And so Q takes on the 2 electrons, and the QH2 now, it's in its reduced form, can move from complex 1 and carry the electron somewhere else. NADH has 2 electrons. It gives them to FMN. It passes them through a bunch of iron sulfur centers. Finally, we get those 2 electrons to Q, and Q is now reduced to QH2, and QH2 can leave and take those electrons somewhere else. Consequently, they're not taking them to complex 1, they're taking them to complex 3. And so what we've seen is the electrons. So let me draw this again. The electrons were in 1 electron carrier and went slowly downhill to other electron carriers, FMN, and the iron sulfur centers, and then finally to Q. And every time that they transfer those electrons, they release some energy. So energy was released. When that energy was released, by some magic that we're not going to go over, that fueled the pumping out of 4 protons. All right, so we went in a stepwise motion. We went to different molecules that had a higher and higher affinity for electrons, and every time we stepwise transferred those electrons, we released a little bit of energy, and that energy fueled the pumping out of 4 protons. So remember that we pumped out 4 protons. And now we created this electrochemical gradient. And the matrix side now is called the N side because it's more negative, because we did what? We lost 4 positive charges. And so now the intermembrane space is called the P side because it's more positively charged because we pumped out those protons. And where do we get the energy to pump out those protons? By the energy that was released every time we transferred electrons. So then in summary for complex 1, it is actually a proton pump. We transferred electrons from NADH to FMN to iron sulfur centers, now to ubiquinone, which we'll look at in a second. It's also called Q. When we did that, let me just erase that. When we did that, we transferred those electrons to ubiquinone. It was accompanied by a transfer of 4 protons, which we just saw from the matrix. And so now the matrix is the N side, the negative side, and the inner membrane space is the P side, the positive side. And if we look at our net equation, we would say that if we put in an NADH and a Q, a ubiquinone cofactor, and 5 protons, one that was already from NADH and H+, and 5 protons from the N side. And now we have NAD+, QH2 took on those 2 electrons, plus 4 protons on the P side. All right, and so very, very briefly, just a closer look at why these electrons are being transferred from one molecule to another. And a simple way to remember it is that we're transferring from, say, NADH, which has a lower affinity for electrons, to Q, which has a higher affinity for electrons. And we can tell that by their their reduction potentials. So this is just a chart of the the reduction potentials. So we see our reduction potentials, and if we look, those with the lowest reduction potentials are usually going to give electrons to something with the higher reduction potentials. And if we look here at NADH, where we started, it has a reduction potential of negative 0.32. Then we transferred it to FMN, the NADH dehydrogenase complex. It has a higher reduction potential. So it makes sense that we go from NADH to FMN. And then we say an even higher reduction potential is ubiquinone. When it gets reduced, it's ubiquinol. It has a positive or even higher reduction potential, basically meaning it has a higher affinity for electrons. So then as we transfer those electrons, we're always going to see the electron transfer from something with a low electron potential or reduction potential to something with a higher reduction potential. And we know that our end goal is to get those electrons to oxygen. So oxygen has a very high reduction potential. So that's the last place where we're going to transfer those electrons. So going from NADH to FMN to ubiquinone, or Q, makes sense because we're going from a low reduction potential to a higher reduction potential. And then we're going to see in our other complexes that we're going to go from cytochrome C to cytochrome C1 to cytochrome C. They have higher and higher in a stepwise fashion reduction potential. And then we're going to finally get it to oxygen, which has the highest reduction potential. Kind of makes sense if you think way back to our periodic table that oxygen is right next to fluorine, and it really likes electrons. It's very electronegative. And this is not really terms you would talk about in biochemistry, but just to bring your mind back to something you learned already, things with high electronegativities really like electron. So oxygen is one of the most electron-loving elements they are, so it would have a high reduction potential. So let's look at some of these electron carriers. The first electron carrier that we saw was NADH. So we've seen the structure of that in the past. We've seen the structure of FMN. They kind of both just look like nucleotides. And then we said after they leave the FMN, their electrons are transferred to the iron sulfur centers and then finally to Q, or ubiquinone, in complex 1. All right, so let's look at the structure of first the iron sulfur centers and then ubiquinone. They're found in several proteins in the electron transport chain, so we'll see these iron sulfur centers in complex 1, 2, and 3. And they basically are bonded to cysteines, have irons and sulfurs. You don't have to know too much about this, but irons and sulfurs bonded to cysteines within the enzyme complex. These can only take one electron at a time, so we'll go through many iron sulfur centers, taking those 2 electrons one at a time. So one electron goes here, and one electron goes here, and one electron goes here into those iron sulfur centers. And then we're going to be subsequently reducing each of these irons, or iron 3 pluses, to iron 2, and transferring those electrons until finally in the complex we get to ubiquinone. So we finally made it, and we transferred those electrons one at a time through those iron sulfur centers, and we got to our last electron carrier, which is ubiquinone. It's also called coenzyme Q. If you go to the drugstore, you'll see coenzyme Q. And so this is what coenzyme Q is. It's a lipid-soluble conjugated dicarbonyl compound that readily accepts electrons. And we saw from the electron, the reduction potential, that it likes electrons. So it accepts those 2 electrons. It also picks up 2 protons to give an alcohol that's ubiquinol. So this first one, you don't need to know the structure of this, but just to show you, we have ubiquinone, and then lastly ubiquinol, which gives us 2 alcohols because it took 2 electrons, but it also took 2 protons. Now, ubiquinol can freely diffuse in the membrane, carrying the electrons and the protons from one side of the membrane to another side of the membrane. So this one can freely diffuse the membrane, and so we'll see it as an electron carrier, the ubiquinol, carrying these electrons that it got from NADH to complex 3. Okay, so we're still transferring electrons and we're pumping out protons. And so we're done with complex 1. We already did that. We transferred some electrons from NADH to NA, and it created NAD+, and finally the electrons are sitting here in coenzyme Q. All right, so that complex is called the complex 1 NADH dehydrogenase. Again, you don't have to know the name. It's just complex 1. And now we need to go to complex 2. Complex 2 is succinate dehydrogenase. You've already actually seen succinate dehydrogenase. And it's going to transfer electrons from FAD H2 to ubiquinone. So let's look at that. So complex 2 is the succinate dehydrogenase. And so we've seen succinate dehydrogenase in the citric acid cycle. So it's the exact same reaction where we take a succinate that's created in the citric acid cycle. We transfer 2 electrons, because we're going to create this double bond here, to FAD. We're going to get FADH2. So FAD accepts 2 electrons from succinate. We saw that in the citric acid cycle. And then where are they going to give those electrons to? So we're going to transfer the electrons from our FADH2, and then those electrons are going to be passed just like before. It's the same reaction to our iron sulfur centers. So now we're passing electrons from succinate to FAD to FADH2 to our iron sulfur centers, and then finally to ubiquinone. So it's the same reaction as before, except for we're utilizing the succinate as our electron giver, what gives the electrons to FAD. And instead of FMN, we're going to create FADH2. FADH2 is going to pass electrons through one at a time through our iron sulfur centers, and then lastly to ubiquinone. And we're going to create ubiquinol which is QH2. So the reactions of complex 1 and complex 2 are the same, except, and this is a very big exception, we're not pumping out protons. So this time we have our QH2 carrying these 2 electrons, and it can freely diffuse across the membrane. It can carry those electrons to complex 3. But in this case, we're not pumping any protons. We just have the electrons sitting in QH2. So QH2 is carrying 2 electrons. All right, so now we're going along our electron transport chain. We did complex 1. Check, we took the electrons from NADH and we passed them to Q. So Q has these electrons as QH2. Complex 2 is not connected to complex 1. It's a different complex in that it takes electrons from succinate and creates an FADH2, and then it eventually passes those electrons to QH2. So now we have 2 QH2s, one from complex 1, one from complex 2. And now those QH2s are going to pass electrons to complex 3. So we've done complex 1, we've done complex 2. Now we need to pass those electrons from QH2 that was created in complex 1 and 2 to complex 3. And complex 3 has a very long name. No one will ever say this name. It's just called complex 3, or our ubiquinone cytochrome C, oxidoreductase cytochrome C. So I want to stop for a second and look at the structure of cytochrome C. We have from complex 1 and complex 2, we have our electrons being carried by ubiquinol. All right, and eventually we know we want to get them to oxygen. And so our complex 3 and complex 4 are going to have cytochromes as their electron acceptors. Now, because they're in ubiquinol, we're going to go into some electron acceptors with a little bit higher reduction potential. So you've seen something that kind of looks like this before. It looks kind of like a porphyrin ring. It has an iron center. And so cytochromes are soluble heme-containing proteins found in several of our electron transport chain complexes. And they can freely move in the intermembrane space. So the heme iron can either be iron 3+ or iron 2+, and they can accept 1 electron at a time. So this is just to bring your attention to now we're moving to electron acceptors with higher reduction potential in our complex 3, in our complex 4, until we finally get to oxygen, which is the ultimate electron acceptor in our complexes. So now we're carrying our electrons that, again, we got from FADH2 and NADH to complex 3, which has cytochrome as electron acceptors. And so our QH2, which can freely diffuse, has accepted these electrons and is carrying these electrons from complex 1 and complex 2 to reduce the molecule cytochrome C. So this is a lot going on. It's just to show you that we have a transmembrane complex or transmembrane protein, and that transmembrane protein is accepting electrons from QH2 or our ubiquinone in its reduced form, and it's passing along those electrons to our cytochromes. So we have many cytochromes, we have many iron sulfur centers, a whole lot going on. But finally, our ultimate acceptor of those 2 electrons from QH2 is going to be cytochrome C. Cytochrome C. And so experimentally, we found that 4 protons are transported across the transmembrane per 2 electrons that reach cytochrome C. So 2 from Q2 QH2 from the matrix. And so as we pump those electrons or transfer those electrons from QH2, which came from complex 1 and complex 2, we're going to have 4 protons that get pumped across the into the p side, into the intermembrane space. So our net equation for that would be, we started with 1 QH2, and that QH2 can come from complex 1 from the NADH, or complex 2 from the FADH2, with 2 cytochrome C1s and 2 protons. And then Q has released those 2 electrons, so now we have Q, we have cytochrome C, but we also have 4 protons. So where are our electrons now? Our electrons are being carried by cytochrome C. It doesn't really matter what cytochrome it is. Cytochrome C, B, A, whatever. Eventually we got to a cytochrome. And we have our 2 electrons being carried from NADH or FADH2 in our cytochrome, but also we have added 4 protons to the intermembrane space. So that's going to be important. We have 4 protons pumped over in complex 1, and now we have 4 more protons being pumped to the p side for complex 3. Okay, so we have passed along electrons from complex 1, our NADH dehydrogenase, our complex 2, our succinate dehydrogenase, to QH2, and QH2 takes those electrons to complex 3, and finally we have those electrons being carried by cytochrome C. So cytochrome C is going to take those electrons to complex 4. So now here we are in complex 4, which is called cytochrome oxidase, and our final electron carrier is going to be oxygen, or electrons acceptor is going to be oxygen. So again, we've moved that from complex 3. Our electrons are being carried by cytochrome C, and the cytochrome C is going to interact with complex 4, which is called cytochrome oxidase. Alright, so our complex 4, or cytochrome oxidase, interacts with cytochrome C. Now cytochrome C has 4 cytochrome Cs are carrying 4 electrons, 2 from each QH2 from complex 1 and complex 2. The mechanism or the pathway for this is so unimportant, we're going to skip it altogether and say that those 4 electrons are used to reduce 1 oxygen molecule to 2 water molecules. So oxygen is somewhere in this cytochrome oxidase, and eventually, so oxygen goes into this complex 4, and we get 2 water molecules. So 2 oxygens gives us 2 water molecules, each having 1 oxygen. But of course, 2 water molecules also have hydrogen in it, so we just pick up 4 protons. There's a lot of protons sitting around. They pick up 4 protons from the matrix. So now we're reducing even more the amount of protons, so the inside is getting even more negative. Additionally, by some mechanism no one knows, there are 4 protons pumped into the intermembrane space. All right. So what do? We created 4 cytochrome Cs from the 2 QH2s. The 4 cytochrome Cs dump these electrons into complex 4. Complex 4 was able to reduce oxygen to 2 water molecules, and of course water has hydrogen in it, so we also had to include 4 protons from the matrix side. So 4 protons were taken to make 2 waters, and also 4 protons were pumped out into the intermembrane space. So now we've completely transferred all the electrons that we're going to transfer to NADH, and FADH2. We have our byproduct, which is water, and we pumped a whole lot of protons out into the intermembrane space and also use some of those protons to make our water molecule. Okay, so in summary, for the electron transfer just from an NADH, we would have NADH that's on the matrix side, 11 protons on the matrix side as basically our reactant, one coming with the NADH, since that was kind of connected to the NADH in the beginning, and then 10 others were pumped over to the intermembrane space. So we have our 10 others pumped over into the intermembrane space. And in the end, those electrons from NADH were passed into one oxygen, but we don't write O, we always write half O2. And then we created a water. So in the thoughtfulness of time, I'm not going to go through each step of how did we end up getting 11 protons pumped out from the inside and 10 protons on the P side, but it's kind of a fun activity to do. We end up with a surplus of 10 protons on the P side, and that is going to set our electrochemical gradient where we have more protons on the P side and less protons on our N side. So now it's negative, and that is going to help to give the energy needed to synthesize ATP. So right now we have a model for the synthesis of ATP, and it's driven by the proton motive force. And so if we look at our intermembrane space and our transmembrane proteins, we see complex 1, complex 2, complex 3, complex 4. But just upstream from that, we have our ATP synthase, or our complex 5, but it's always called ATP synthase. And so when we have created this electrochemical gradient, we have all these extra protons, 10 extra protons just from NADH in the intermembrane space. And they really want to get back, I'll just draw that, because we have more positive protons in the membrane space than on the matrix side. They really want to get back into the matrix to get in an equilibrium. And so as they shove themselves or transport themselves back into the matrix side or the inside, that's going to give enough energy for this motor. So this is kind of like a motor. The ATP synthase is going to drive the synthesis of ATP, which is a condensation of ADP and phosphate. So now orient yourself and think about, okay, we have all these protons, they're sitting on the intermembrane space. As they try to flood back into the matrix through our ATP synthase protein, when they do that, that's going to give energy to make conformational changes in our ATP synthase protein, and that's going to be the driving force in condensing ADP and phosphate to make ATP. So in the step 1, we transported electrons. So we finally got electrons into making water molecules, and that's going to be a byproduct, and you're just going to pee that out. So that's done with. But the point of it was to do step 2, is that we're going to use not the electrons but the proton gradient to actually fuel or give the energy for ATP synthesis. So now we're at the ATP synthase, or complex 5. It's called complex 5, but you should remember that it's called ATP synthase. Alright, so this is the structure of ATP synthase. I don't really like this figure because it's kind of upside down from what we've been talking about. But so just to orient you, this is the intermembrane space and this is a matrix. And the P side, we spent a lot of time with complex 1, 2, 3, and 4 creating a proton gradient, or more protons on the P side, and less protons on the inside. And so those protons, if they have any chance to, they're going to pump themselves back into the matrix side because there are less protons over there, and that's just osmosis. All right, so our ATP synthase has two different basic parts and two different functions. It has an FO, so it has an FO, and this is going to be our intermembrane space. This is FO. And then it has an F1. So sometimes it's called FOF1 ATP synthase. And our FO is the proton channel. And so we know that the intermembrane space is impermeable to everything. And so the only way that the protons can actually get back into the matrix is through a proton channel. So now it's a channel, it's not a pump. Is somebody lets them through. And so they're going to go through this proton channel that's part of the complex 5 or the ATP synthase. And it opens a pathway for protons to go through. But as it does that, it actually rotates. So we'll see as protons start to pass through the FO part of the ATP synthase, it's going to cause a conformational change or a rotation. As this rotates, we're going to see some conformational change in the F1 side, that's on the matrix side. So protons are going to cause a conformational change, which is a rotation of FO. As FO rotates, we're going to see conformational changes in the F1 side, which has all these subunits, 3 alpha subunits and 3 beta subunits. All right, so each subunit is going to take a turn actually taking in an ADP and a phosphate. And as it rotates, it's going to condense the ADP and that phosphate together to create ATP, and then the ATP is going to be released. So it's a very kind of complex mechanism to just see in 2D. So I want you to take some time to watch this video of how this motor kind of acts to rotate as the protons go through, take in ADP and phosphate in the beta subunits, and then release them as ATP. Okay, so what you just hopefully watched was a rotational catalysis. The proton motive force, that means the protons, actually 3 protons on the P shaft, on the P side, go through the channel of FO and they come out on the inside. And when that happens, that rotates the gamma shaft on the F1 domain. As that happens, this causes a alpha beta dimer to come in contact with the gamma shaft. So we have here, if we start up here, we have an alpha domain and we have a beta domain, or alpha subunit and a beta subunit. And the beta subunit is where the catalysis is going to happen. It contains, because there are lots of free floating around adenosine diphosphates and phosphates. And so the ADP and the PI are going to be in the beta domain. And as we have this rotational shift, because we have an influx of protons, that's going to cause the ADP and the PI to come into contact with each other in such a way that they form an ATP. This is also going to cause a rotational shift in that the ATP in the other beta domain gets released, because it likes to hold on to ATP, but it doesn't like to release it. So as we have the protons going through the channel, it's going to cause conformational change where we can actually make an ATP and then release an ATP. And as 3 more protons go through, we're going to cause another rotational change where we have ADP that's in one beta subunit get together with a phosphate and we form ATP, and then the ATP, wherever it is in the beta subunit, can be released. And so that just keeps happening where the protons come in, the protons go out of the channel, and we have the condensation of ADP and phosphate, ATP release, condensation ADP and phosphate, ATP release. But that happens when every 3 protons go across the intermembrane space or channel. Okay, so there you have it. You have the electron transport chain where the electrons are moved from NADH or FADH2 to QH2, then to cytochrome C, then to oxygen. We have our byproduct being water. And then we created our electrochemical gradient where we had protons in the intermembrane space. Those that excess of protons get channeled back through into the matrix side, and that helps the rotation of the FO membrane subunit of ATP synthase and the creation of ATP. So this was a little bit long. I will do another review of everything and some summary of everything in the next lecture. Here is a nice song to help you remember some of the events that are happening in the electron transport chain. I hope you listen to it. I hope you enjoy it. It's been a very interesting semester, and this is my last lecture, and I will miss you all, and I hope that you stay healthy and get closer to Christ. See you next time.